Hey, glad you're here. Good morning. Welcome. We are finishing up section 7.1.7. So the 7.1s are done after today. And I'm replacing a good chunk of what would normally be classwork with some exercises that you're going to do in Delta Math. I think there's about 6, no more than 8, but there's 6 to 8 exercises in Delta Math where you'll be doing some proofs. Remember, doing this requires kind of a growing list of reasons. I'm kind of keeping a list of mine. This is the list that I've been building this year of things that as we encounter them, I'm either modifying it or adding to it. So like I said, having your own composition notebook, a place that you can flip to and remind yourself of things that are true in a geometric context. There's a few problems that we're going to do before I say jump to Delta Math, and let's look at a couple of those. So one of them is, let's go to this next page, is these 3, and I'm just going to ask you to for each one of these solve for x. So my suggestion is right now that you go ahead and pause the video, solve, and then come back. So you should pause. Okay, so the solution to this one is because these two angles at the bottom are 40 degrees, it's the inverse of that isosceles triangle theorem, right? If you have an isosceles triangle, the angles across from the congruent sides are equal, but the converse of that is if you've got a triangle in which 2 of the angles are congruent, the sides across from those have to be congruent to each other also. So the 3x plus 13 is the same as 5x plus 2, and x should be 5.5. Let's go to the next one. Oops. So on this next one, go ahead and pause it. Okay, so a lot of ways we can look at this problem. This angle here that I've labeled as 7x minus 3, that angle is a corresponding angle to the angle that's right here. So because those two angles are corresponding angles, they have to be congruent to each other. So I could say this angle must be 7x minus 3 also. Now, I can do that because these lines are shown to be parallel, right? So because the parallel lines are parallel, this angle must be the same as this one. Now, what that gets me is now I have 2 angles that are adjacent to each other that form a linear pair, right? And angles that form a linear pair have to have a sum of 180 degrees. So it's not that these 2 angles are congruent to each other, but they have to add up to 180. And because of that, you get an expression like 7x minus 3 plus 4x plus 12 has to be equal to 180, so x is 15.55. Let's take a look at the next one. So on this, again, whenever we're shown parallel lines, so this line is parallel to this one, we're thinking of what congruent angles do we have. Well, if this is 110, this angle right here has to also be 110. And there is an exterior angle theorem I could use, or I could just think about, okay, this is 110, this is x. If this is 140, the angle inside has to be 40. So I have 3 angles here, right? I've got 110, I've got a 40. So that leaves a value for this. This angle x has to be 30. I don't know if I said pause. I'm sorry, I just went through that. So that's that one. Okay, so let's move forward and let's talk about this problem. And this is a flowchart proof. We've seen something like this before. Oops, let me move forward here. So I think this is exactly what's in your textbook. We're told that E is a midpoint of 2 different things, right? E is a midpoint of BD and E is a midpoint of AC. So because E is a midpoint of both of those, we know certain things have to be true. So I think I can write on this. So because E is the midpoint of BD, I know that this segment and this segment are going to be congruent because a midpoint cuts a segment into 2 congruent segments. And because E is the midpoint of AC, I know that this segment and this segment have to be congruent. And if we look at it, we have a very nice pair of congruent sides, right? They've already labeled these, right? The AE is congruent to CE, definition of a midpoint. something very similar could be reflected over here because E is the midpoint of BD, right? There are two segments that are congruent, definition of midpoint. And the only other thing that we would have to point out is that this angle, right, is congruent to this angle because they're vertical angles. And remember, at vertex E, there's a lot of angles hanging out there, so we have to use the correct names for them. So we could say, for example, angle AEB is congruent to angle, I did AEB, so I could do CED, angle CED. And the reason why is they're vertical angles. And vertical angles are always congruent. So whenever we have two lines that intersect, the lines that are right across from each other, either this way, or just the ones that are across from each other, have to have equal measure. So at this point, these two triangles are congruent by side angle side. So we would just include that in the proof. One last thing we'll look at, just for a way of reminder, and then you can jump into delta math. Let's go over here. So we have this diagram, and I would like for us to construct a proof of this. And one of the things that I can see from the diagram is that I have a pair of parallel lines. Now, this is impossible, and I dislike it when our book does this, but they've given me a situation where they didn't include any letters on the diagram, so feel free to add your own, but I'm going to add these. So I have these letters right here, and because I have a pair of parallel sides, and I know that they're parallel because of these angle marks that were included in the diagram, right? Because I know those are parallel, I know that there's a pair of congruent angles that are lurking that could be useful. So remember, parallel lines, right, should give rise to some congruent angles. And in this case, the angles that are congruent are the ones that live here and here. Those are alternate interior angles. So I could say, because those lines are parallel, these alternate interior angles, right, angle CAB lives here, is congruent to angle, what did I put, ACD, which lives here. So those two angles are congruent to each other because they're alternate interior angles and the lines were parallel. Another thing that's true in this diagram is they give me a pair of congruent sides as well. So we don't always see this, but in this diagram, and the diagram is very deceptive, right? They're telling me that not only are these lines parallel, right? The parallel is because of these arrows, but they're also telling me that these sides are congruent because of the tick marks. So although it looks nothing like that, we could say that it must be the case that segment AB is congruent to CD because that's given, right, with the tick marks. Again, does not look like that at all. So at this point, what I have is I have a congruent side, I have an angle, a congruent side and an angle, and they happen to share segment AC. So it's going to be an application of the reflexive property. So because AC is congruent to itself by the reflexive property, we have everything that we need at this point to claim that these two triangles are congruent by side angle side. And in fact, the triangles would be, you could say DCA, D to C to A is congruent to B to A to C. And the reason those are congruent is by side angle side. So that's it. I just wanted to have a couple examples that I could talk through with you, look at some things. And the exercises that we are replacing are these. And just again, I encourage you to think about your list of reasons, things with isosceles triangles, midpoints, bisectors. If you see parallel lines, we're looking for pairs of congruent angles that might be useful. So go ahead and finish up the exercises in Delta Math, and then go ahead and start the review preview set for tonight. This is Mr. Roberts. I'm glad you're here. And I hope you have a good day.